What is natural gas? Natural gas is a fossil fuel energy source. Natural gas contains many different compounds. The largest component of natural gas is methane, a compound with 1 carbon atom and 4 hydrogen atoms, CH4. Natural gas also contains smaller amounts of natural gas liquids, NGLs, which are also hydrocarbon gas liquids, and non-hydrocarbon gases, such as carbon dioxide and water vapor. We use natural gas as a fuel and to make materials and chemicals. How did natural gas form? Millions to hundreds of millions of years ago, the remains of plants and animals, such as diatoms, built up in thick layers on the Earth's surface and ocean floors, sometimes mixed with sand, silt, and calcium carbonate. Over time, these layers were buried under sand, silt, and rock. Pressure and heat changed some of this carbon and hydrogen-rich material into coal, some into oil, petroleum, and some into natural gas. Where is natural gas found? In some places, natural gas moved into large cracks and spaces between layers of overlying rock. The natural gas found in these types of formations is sometimes called conventional natural gas. In other places, natural gas occurs in the tiny pores, spaces, within some formations of shale, sandstone, and other types of sedimentary rock. This natural gas is referred to as shale gas or tight gas, and it is sometimes called unconventional natural gas. Natural gas also occurs with deposits of crude oil, and this natural gas is called associated natural gas. Natural gas deposits are found on land, and some are offshore and deep under the ocean floor. Natural gas found in coal deposits is called coalbed methane. How do we find natural gas? The search for natural gas begins with geologists who study the structure and processes of the Earth. They locate the types of geologic formations that are likely to contain natural gas deposits. Geologists often use seismic surveys on land and in the ocean to find the right places to drill natural gas and oil wells. Seismic surveys create and measure seismic waves in the Earth to get information on the geology of rock formations. Seismic surveys on land may use a thumper truck, which has a vibrating pad that pounds the ground to create seismic waves in the underlying rock. Sometimes small amounts of explosives are used. Seismic surveys conducted in the ocean use blasts of sound that create sonic waves to explore the geology beneath the ocean floor. If the results of seismic surveys indicate that a site has potential for producing natural gas, an exploratory well is drilled and tested. The results of the test provide information on the quality and quantity of natural gas available in the resource. What happens when natural gas is found? If the results from a test well show that a geologic formation has enough natural gas to make a profit, one or more production or development wells are drilled. Natural gas wells can be drilled vertically and horizontally into natural gas-bearing formations. In conventional natural gas deposits, the natural gas generally flows easily up through wells to the surface. In the United States and in a few other countries, natural gas is produced from shale and other types of sedimentary rock formations by forcing water, chemicals, and sand down a well under high pressure. This process, called hydraulic fracturing or fracking, sometimes referred to as unconventional production, breaks up the formation, releases the natural gas from the rock, and allows the natural gas to flow to and up wells to the surface. At the top of the well, natural gas is collected in gathering pipelines and sent to natural gas processing plants. Natural gas is processed for sale and consumption. Natural gas withdrawn from natural gas or crude oil wells is called wet natural gas because, along with methane, it usually contains NGLs, ethane, propane, butanes, and pentanes, and water vapor. Wellhead natural gas may also contain non-hydrocarbons such as sulfur, helium, nitrogen, hydrogen sulfide, and carbon dioxide, most of which must be removed from natural gas before it is sold to consumers. From the wellhead, natural gas is sent to processing plants where water vapor and non-hydrocarbon compounds are removed, and NGLs are separated from the wet gas and sold separately. Some ethane is often left in the processed natural gas. The separated NGLs are called natural gas plant liquids, NGPLs, and the processed natural gas is called dry, consumer-grade, or pipeline-quality natural gas. Some wellhead natural gas is sufficiently dry and satisfies pipeline transportation standards without processing. Chemicals called odorants are added to natural gas so that leaks in natural gas pipelines can be detected. Dry natural gas is sent through pipelines to underground storage fields or to distribution companies and then to consumers. In places where natural gas pipelines are not available, to take away the associated natural gas produced from oil wells, the natural gas may be re-injected into the oil-bearing formation, or it may be vented or burned, flared. Re-injecting unmarketable natural gas can help to maintain pressure in oil wells to improve oil production. Coal bed methane can be extracted from coal deposits before or during coal mining, and it can be added to natural gas pipelines without any special treatment. Most of the natural gas consumed in the United States is produced in the United States. Some natural gas is imported from Canada and Mexico in pipelines. A small amount of natural gas is also imported as liquefied natural gas. Natural gas is an important and versatile energy source. Understanding the process of natural gas formation and extraction provides a deeper insight into this resource and its significance in supplying energy and raw materials to various industries. Technology and science play a crucial role in the extraction and utilization of natural gas. Advances in geological survey methods and extraction technologies, such as fracking, allow us to efficiently and safely access new energy sources. Sustainable management of natural gas resources is essential to minimize environmental impact and ensure future energy supply. This requires careful extraction and processing practices, as well as the development of environmentally friendly technologies. The extraction and use of natural gas are not only domestic issues, but also involve international cooperation. The interdependence among countries in energy supply underscores the importance of international collaboration to ensure a stable and secure energy supply.
The origins of Earth's water. Humans are deeply intertwined with water. Approximately 71% of our planet is covered by water. Human babies are composed of about 78% water, and adults consist of up to 60% water by weight. Without water, we can only survive for a few days. Water is everywhere on Earth, but where did it come from? Understanding the source of Earth's water can shed light on the origins of life on our planet and offer insights into the presence of water on other worlds, including exoplanets. Numerous theories attempt to explain how Earth acquired its water, which generally fall into two main categories. One theory suggests that Earth was formed with the molecular precursors of water already present. The other proposes that water-laden space rocks, such as asteroids and comets, delivered water to Earth after its formation. These theories are not mutually exclusive. It is possible that Earth's water came from multiple sources. Scientists are continually refining models of the early solar system to better understand the origins of Earth's water. Earth's formation and early conditions. Earth formed approximately 4.54 billion years ago from the residual material left after the formation of the Sun from a collapsing cloud of gas and dust. This leftover material also created the rest of the solar system, including our planet. A key question is whether Earth was born with everything needed to create the oceans, lakes, and rivers that are essential to life. However, the early inner solar system was extremely hot. Any liquid water present at that time would have vaporized and been expelled into space. Water locked in rocks. Water could have been present in the form of hydrogen within the planet's building blocks. A recent study revealed that enstatite chondrites, a type of meteorite thought to resemble the raw materials that formed Earth, contain enough hydrogen to provide at least 3 times the mass of water in Earth's oceans. While the exact timing of this water delivery is unclear, these meteorites closely match the rocks found in Earth's interior. If Earth initially contained water trapped beneath its surface, volcanic activity could have released it as water vapor, which would then condense and fall back to Earth as rain. The Theia impact. About 4.51 billion years ago, a Mars-sized body named Theia collided with Earth. This impact melted part of Earth's mantle and resulted in the formation of the Moon. Some studies suggest that Theia may have brought water to Earth during this collision. Earth's own water production. Another theory proposes that Earth generated its own water. Observations of young exoplanets enveloped in molecular hydrogen suggest a possible mechanism. Modeling by some scientists indicates that molecular hydrogen could interact with magma oceans on young planets, producing substantial amounts of water. Water delivered by asteroids. The early solar system was a turbulent place. Between 4.0 to 3.8 billion years ago, the orbits of the outer planets shifted, causing gravitational disturbances that sent icy space rocks crashing through the inner solar system in an event known as the Late Heavy Bombardment. These impacts could have brought significant amounts of water to Earth. Initially, comets were suspected to be major contributors to Earth's water. However, space missions like Giotto, which visited Halley's Comet in 1986, and Rosetta, which visited comet Churyumov-Gerasimenko from 2014 to 2016, found that the chemical composition of comet water differs from that of Earth's water. This discrepancy has led scientists to focus more on asteroids and meteorites as the likely sources of Earth's water. Evidence from asteroids' analyses of samples from asteroid Ryugu brought back to Earth by the Hayabusa 2 mission revealed that the water locked in Ryugu's rocks matches the type of water found in Earth's oceans. Ryugu's composition is similar to that of Ci chondrites, a type of meteorite that could have delivered up to 30% of the total mass of water in Earth's oceans. In September 2023, NASA's OSIRIS-REx spacecraft returned samples from asteroid Bennu. Preliminary analyses of these samples found water and organic materials, suggesting that asteroids like Bennu could have played a significant role in bringing water to Earth. Continued analysis of these samples may provide further insights into the origins of Earth's water. The significance of water. Although the exact source of Earth's water remains uncertain, its presence is crucial for the development of complex life. Some of the earliest evidence of life dates back to around 3.7 billion years ago, when microbes first adapted to an atmosphere rich in carbon dioxide. These early organisms eventually evolved into cyanobacteria, which utilize water, sunlight, and carbon dioxide to produce food through photosynthesis. This process releases oxygen, which over time led to the oxygen-rich atmosphere web-wreathed today. Raise a glass of water in gratitude to the asteroids, meteorites, molecular hydrogen, volcanic activity, and other processes that may have contributed to bringing water to Earth. Without these sources and mechanisms, life as we know it would not exist. The ongoing research and exploration of our solar system continue to uncover the fascinating story of how Earth got its water, deepening our understanding of our own planet and the potential for life elsewhere in the universe. Water teaches us many valuable lessons about life. First, the patience and perseverance of water, as it erodes rock over time, remind us that small but consistent efforts can lead to great success. Water also demonstrates adaptability and flexibility by existing in various states, teaching us how to adjust and change to fit new circumstances. Though soft, water possesses immense strength, showing that gentleness does not equate to weakness. Water is also a source of life, essential for all living beings, reminding us of the importance of nurturing and protecting life. Its ability to cleanse and purify teaches us about the necessity of maintaining purity in our minds and thoughts. Finally, as part of the natural cycle, water connects all ecosystems, reminding us of the importance of connection and cooperation in life. Antarctica, the southernmost continent, holds the majority of Earth's ice and a significant portion of its freshwater reserves, covering about 14 million square kilometers, 5.4 million square miles. It is home to an estimated 25,400,000 cubic kilometers, 6,090,000 cubic miles of ice. This immense ice mass accounts for roughly 60% of the planet's freshwater and 90% of all its ice. The implications of this ice melting entirely are profound and far-reaching, affecting global sea levels, climate patterns, ecosystems, and human societies. Sea level changes and geographic impact. If all Antarctic ice melted, it would result in a dramatic rise in global sea levels by approximately 70 meters, 230 feet. This rise would drastically alter the world's coastlines, submerging entire regions and reshaping the geography as we know it. Submerged cities and lost land coastal cities across the globe, including major metropolises like New York, Tokyo, and London, would be completely submerged. The state of Florida would vanish entirely beneath the rising waters, and low-lying countries such as the Netherlands, Bangladesh, and Denmark would lose significant portions of their land. Island nations would be especially vulnerable, facing complete inundation and disappearance. In regions like Australia, the rising sea levels would create a large inland sea, fundamentally transforming the landscape. River estuaries would expand significantly, and the paths of rivers would change as floodplains and riverbanks become submerged. This expansion would create new waterways and affect existing aquatic ecosystems. Population displacement. An estimated 40% of the world's population lives within 100 kilometers, 62 miles, of a coastline. The inundation of coastal areas would force billions of people to relocate to higher ground, creating unprecedented levels of displacement and posing significant challenges for urban planning, infrastructure, and resource management. Changes in ocean chemistry. The melting of Antarctic ice, which primarily consists of fresh water, would significantly alter ocean chemistry. This influx of fresh water would decrease the salinity of the oceans and affect various dissolved chemicals and the pH levels of seawater. Impact on salinity and marine life. A reduction in ocean salinity would have complex effects on marine ecosystems. Some marine organisms, particularly those sensitive to changes in salinity, might struggle to adapt, leading to shifts in species distributions and potentially disrupting food webs. Coral reefs, which rely on specific salinity ranges, could be particularly affected, exacerbating the challenges already posed by ocean acidification and rising temperatures. Effects on oceanic currents and climate. Oceanic currents, driven by gradients in temperature and salinity, play a crucial role in regulating global climate patterns. The influx of fresh water from melting ice would disrupt these currents, potentially altering climate systems such as the Gulf Stream and the thermohaline circulation. Such changes could lead to regional climate shifts, affecting weather patterns, precipitation, and even the distribution of heat across the planet. Isostatic rebound and geological effects. The melting of Antarctic ice would trigger a process known as isostatic rebound, where the Earth's crust, previously compressed by the weight of the ice, begins to rise. The mechanics of isostatic rebound. Antarctica, currently weighed down by its ice mass, would experience uplift similar to a heavily laden ship rising in the water when cargo is removed. This uplift would occur over tens of thousands of years, with an estimated initial rise of about 7.5 centimeters per year for the first 2,000 years, gradually decreasing to about 1 centimeter per year over the subsequent 10,000 years. The total uplift could reach up to 400 meters in some areas. Long-term geological changes. This isostatic rebound would lead to significant geological changes, including the formation of new landforms and the alteration of existing topography. The uplifted land would eventually stabilize, but the process would be accompanied by increased seismic and volcanic activity as the Earth's crust adjusts to the new equilibrium. Temperature effects and habitability. The complete melting of Antarctic ice implies extreme global warming scenarios with temperatures rising far beyond current projections. Under such conditions, the tropics would become uninhabitable due to extreme heat, forcing populations to migrate toward the poles in search of more temperate climates. This shift would disrupt agriculture and food production, leading to widespread crop failures and threatening food security. Ecosystem collapse and mass extinction. Ecosystems across the globe would face collapse as rising temperatures and altered precipitation patterns create inhospitable conditions for many species. This would likely result in a mass extinction event, with significant losses in biodiversity and the disruption of ecological networks that support human life. Historical context. The last ice-free Antarctica. The Antarctic ice sheet began to form around 35 million years ago, during a period when global temperatures were about 4 degrees Celsius higher than today. Before this ice formation, Antarctica experienced different climatic conditions and ecosystems. The isolation of Antarctica over the South Pole and the development of the circumpolar current, resulting from the drift of South America away from Antarctica, contributed to the continent's cooling and the formation of the ice sheet. This current prevented warm water from reaching Antarctica, allowing the ice to accumulate. During the late Cretaceous period, approximately 90 million years ago, Antarctica was covered with temperate rainforests, similar to those found in present-day New Zealand. These forests thrived in a warmer climate, with high levels of carbon dioxide, 1,120,680 ppm, and long periods of darkness during the polar night. The transformation from a temperate, forested continent to an icy wilderness highlights the dynamic nature of Earth's climate and geological processes. potential large-scale melting events. Current scientific observations and models suggest that parts of Antarctica, particularly the Thwaites Glacier and the West Antarctic Ice Sheet, WAIS, are vulnerable to significant melting. The Thwaites Glacier, located in West Antarctica, is a critical area of concern due to its potential to collapse in the coming decades. If this glacier were to melt completely, it could contribute around 65 centimeters 2 feet to global sea levels. This possibility underscores the importance of monitoring the glacier to understand the mechanisms of ice sheet collapse and to prepare for potential sea level rise. The WAIS, which includes the Thwaites Glacier, could also collapse over a longer time frame, potentially raising sea levels by about 4 meters, 13 feet. The stability of the WAIS remains uncertain, with predictions suggesting that significant changes may not become clear until 2100 or later. The likelihood of complete Antarctic ice melting. Despite the alarming potential consequences, the complete melting of all Antarctic ice remains highly unlikely within the next several hundred years. Even under extreme climate scenarios, it would take a prolonged period of sustained warming to melt the entire ice sheet. Current climate models project significant ice loss in Antarctica due to rising temperatures, but they do not predict total melting. Mitigation efforts, including reducing greenhouse gas emissions and enhancing climate resilience, are crucial in preventing the worst-case scenarios of ice melt and associated sea level rise. Addressing the challenges posed by Antarctic ice melt requires long-term strategies focused on sustainable development, environmental conservation, and global cooperation. By understanding the complex interactions between ice sheets, climate, and human activities, we can develop effective policies to mitigate the impacts of climate change and preserve our planet's future. The hypothetical scenario of all Antarctic ice melting presents a stark reminder of the interconnectedness of Earth's systems and the profound impact of climate change. While the complete melting of Antarctica is unlikely in the near future, the potential consequences underscore the importance of proactive measures to address climate change and protect vulnerable ecosystems and communities. As we continue to study Antarctica's ice dynamics and monitor changes in the region, it is essential to integrate scientific knowledge into policy decisions and public awareness. By doing so, we can build resilience against the challenges posed by a warming world and ensure a sustainable future for generations to come. If all the ice in Antarctica were to melt, the environmental consequences would be severe and widespread globally. First, the global sea level would rise by approximately 70 meters, 230 feet, leading to the flooding of numerous coastal cities, erasing many low-lying nations, and displacing billions of people. The chemical composition of the sea would also become a concern, as fresh water from the melting ice would reduce ocean salinity, impacting marine ecosystems and potentially disrupting critical ocean currents that influence climate. Additionally, the disappearance of the ice would trigger isostatic rebound, causing the Antarctic continent to rise due to the loss of ice weight, a process lasting tens of thousands of years and potentially leading to significant geological changes. The temperature effects from the ice melt indicate that global temperatures have risen significantly, surpassing extreme climate change scenarios, making many tropical regions uninhabitable and causing ecological disasters such as crop failures and mass extinctions of various plant and animal species. This scenario underscores the importance of mitigating climate change, protecting sensitive ecosystems, and enhancing adaptation measures to safeguard humanity and biodiversity from potential consequences. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.